Hi, I'm Palni Pranesh Mahadevan, a graduate student from the Department of Electrical and Computer Engineering at the University of Florida, Gainesville. And this is a presentation of my final project for the course EEL 6825 Pattern Recognition. My instructor for the course was Dr. Depang Wu. The topic that I've chosen for the final project is evaluation of tracking algorithms used in real-time video tracking. So I will be first talking about what is meant by tracking and the importance of tracking, followed by the complexities involved in tracking objects in videos, and then giving a brief description of the different methods of object tracking that have evolved over the years, followed by the general flow of operation for any tracking algorithm or tracking process. Then give a brief explanation of state space modeling and the two algorithms that I'm going to consider, followed by a final evaluation of the algorithms with a few test cases. What is tracking? Tracking is the problem of generating an inference about the motion of an object given a sequence of images. Object tracking is one of the most important tasks in the field of computer vision. So, why is object tracking so important to us? As we know, object tracking has a wide range of applications across various domains like surveillance, automated video analysis, vision based control, human computer interfaces, robotics, video compression, and medical imaging. Most common ways of representing objects in videos are in the form of points, silhouette, or contour, and also skeletal models and articulated shape models. So, object tracking in video surveillance involves segmenting an object of interest from the scene and estimating the trajectory of the object throughout the course of its motion in the frames, keeping track of the orientation and occlusion in addition to its path of motion in the subsequent video frames. So, any algorithm, any tracking algorithm in general should be designed to assign consistent labels to these objects under objects which are actually the target, the objects that are to be tracked in every frame of the video. Now let's look at some of the complexities involved when it comes to tracking objects in videos. The first thing that comes to our mind is obviously the noise in the environment. Some of the complexities involved, some other complexities are complicated object motion, same object returning after a while into the frame. That has to be tracked properly. It has to be classified as the same object. We should identify the object when it enters the frame again. Similarly, partial and full object occlusions and complex shapes of objects while in motion, like if we are tracking an object such as a human under motion or an animal that is moving, then there is also a change in the shape of the object combined that has to be taken into account when the object is in motion. So these are the complexities that have to be kept in mind. Now, what is occlusion? So if you're developing a system which tracks objects, let it be anything such as people, cars, or a ball, then occlusion occurs if an object you're tracking is hidden by another object. Let's, for instance, if two people are walking across each other, if then one person goes behind the other, then you actually can't see the person behind, but you should still, if that is the person you're tracking, then you should continue tracking the person even if he's hidden behind another object, like a car that drives under a bridge. So that is what occlusion is. All these problems pose a threat to any object tracking algorithm, which can be made simple if certain assumptions can be made regarding the shape, appearance, size, constant acceleration or velocity, and no abrupt changes of the objects to be tracked. So these assumptions being made, various algorithms have been proposed over the years to overcome these problems. Each method uses a different approach towards object detection, real-time tracking, and analysis of the location. So we will be looking at some of the methods that have evolved over the years. Yeah, object tracking can be classified into point-based tracking, kernel-based tracking, and silhouette-based tracking. The point tracking method involves formulating the object to be tracked as points across the frames, which is a complicated problem when there exists occlusion, misdetections, entries, and exits of new objects of the same object which is under study. They can be further classified into deterministic and statistical models. Deterministic models involve qualitative motion heuristics to constrain the correspondence problem, whereas statistical methods take the object measurement explicitly and consider uncertainties to establish correspondence. The next method is the kernel-based tracking method, which is performed by calculating the motion of the object, which is based on representing the object region that is primitive from one frame to the other. These are classified into template-based, multi-view-based tracking. Template-based is searching for the template of the object defined in previous frames, and multi-view-based involves tracking objects with different views. The silhouette-based tracking is majorly used when the complete region occupied by an object is very important. Regions of complex shapes like human body parts can be accurately measured by this method. All these methods create a route for an object over time by tracking its position in the video frames by first identifying its position by object detection methods in the initial frame, and then this will be used to find the region of interest in the frame. Then tracking is done through correspondence across the frames iteratively, updating the object position obtained from the previous frames. This is the general flow of operation for any tracking algorithm. First, the idle image is the image which is initially acquired, which is the first frame of the video. The object to be detected, that is the target object, is identified, and then the subsequent frames are acquired. If the object is found in the subsequent frames, then it goes back and it gets the next frame and continues tracking the object. Otherwise, it goes back to find the object from the same frame. Now, what is state space modeling? Any object in motion can be determined from a video sequence by intensity variations of pixels in the images across the frames, and it can be shown in the state space form as below. This is basically a matrix representation of the state space modeling, where vxk plus 1 and vyk plus 1 are the x and y coordinates of the velocity at the instant, and vxk and vyk are the velocities at the previous instant. Similarly, xk and yk are the x and y coordinates of the center of the object at the previous instant, the object to be tracked. And xk plus 1 and yk plus 1 are for the current instant. Gx and gy are the accelerations in the x and y directions. When the object is under normal translation, that is moving horizontally with respect to the ground, then its acceleration in the y direction or the acceleration due to gravity is assumed to be 0. Whereas when the object is moving vertically with respect to the ground, that is, it's moving vertically with respect to the ground, its acceleration in the y direction is given and the acceleration in the x direction is assumed to be 0. This is given by the following equation. The equation takes the x and y coordinates of the centroid of the object as the elements of measurement vector, where zk is the measurement vector and vk is assumed to be 0 mean white Gaussian noise with covariance rk, which is also known as the measurement noise covariance. The measurement equation can be given as follows. So one of the algorithms we will be considering is the mean shift algorithm. The mean shift algorithm is based on the histogram estimation of the image in the video. So consider a set S of n data points xi in the Euclidean space X. Let k of x denote a kernel function that indicates how much x contributes to the estimation of the mean in the sample. Then the sample mean m at x with kernel k is given by the following equation. M of x is the mean. The difference between m of x and x is called the mean shift. This is iteratively calculated to move the data point to its mean. In each iteration, x tends to m of x, and the algorithm stops when m of x equals x. Suppose let the sequence x, m of x, m of x be called the trajectory of the x, which is the object under consideration. If the sample means are computed at multiple points, then at each iteration, update is done simultaneously to all these points. Mean shift algorithm is a non-parametric statistical method which was put forward by Fukunaga in 1975. And the tracking algorithm, which is based on mean shift object based on color histogram model, was first proposed by Bradsky. Now let's look at the mean shift algorithm, use of the mean shift algorithm in tracking. The first step involved in mean shift tracking is to choose the object or the region to be tracked in the initial frame of the video. This can be represented by a rectangle which surrounds the object. So after choosing the object under object in interest, then we model the object using color probability density in the initial frame. Then the target region is tracked in the video by matching color probability of the target with that of the object model. Mean shift algorithm doesn't use target motion, direction, or speed information in the process of object tracking. The object's color distribution is basically represented as a histogram using mean shift to find out the region that has most similar color distribution. Mean shift algorithm is a non-parametric statistical method which can make rapidly optimal matching during object tracking. It is a non-parametric and iterative procedure to search a local maximum of a density function. So it is suitable for real-time tracking system. A mean shift object tracking based on color histogram model was first proposed by Bradsky, which was already said earlier. MSA would track an object by creating a map corresponding to the new image based on the color histogram of the object in the previous image. Calculate the mean shift to find the peak of the confidence map near the object's previous position. Suppose if the tracking of the object is to be done in a new frame, then the tracking is done in such a way that it searches for the object somewhere close to the object's presence or position in the previous image. So basically it uses the color projection of each frame image by color histogram to adjust the location and size of search window adaptively. Get the best central position as the center of the target by iterative convergence. So the whole process involves the algorithm maximizes the correlation between the histograms of the previous and the current image. The whole process involves histogram extraction, weight computation, and derivation of a new position of a object. So the correlation between the object in the previous and the current frame is given by the Bhattacharya distance. Now what is the Bhattacharya distance? In statistics, the Bhattacharya distance measures the similarity of two discrete or continuous probability distributions. It is closely related to the Bhattacharya coefficient, which is a measure of the amount of overlap between two statistical samples or populations. So using the Bhattacharya distance here, we can calculate the correspondence of the probability distributions of the object under consideration in the current image with the object under consideration in the previous image. This is the algorithm which is used for tracking based on mean shift algorithm. Given QU, the location of the target in the previous frame, we first initialize the location of the target in the frame as Y, and then compute the probability distribution for the current for the object in the current frame using the equations, compute the weights, and then apply mean shift and compute the new location Z given a window size related to H by using the following equation. Then we use these equations to validate the target's new location in the subsequent frames, and then if Z is minus Y is small enough, then we stop. Basically, if Y and Z round off to the same pixel, we stop. Otherwise, we go back to step 1 and continue. Another algorithm we are considering is the Kalman filter algorithm. Now, what is a Kalman filter? Kalman filter, also known as linear quadratic estimation, is an algorithm that uses a series of measurements observed over time, containing statistical noise and other inaccuracies, and produces estimates of unknown variables that tend to be more precise than those based on single measurements alone. This filter was named after Rudolf E. Kalman, one of the primary developers of this theory. The Kalman filter has various applications in technology. A common application is for guidance, navigation, and control of vehicles, particularly aircraft and spacecraft. Furthermore, the Kalman filter is also widely applied concept in time series analysis used in fields such as signal processing and econometrics. Kalman filters also are one of the main topics in the field of robotic motion planning and control. And they are sometimes included in trajectory optimization too. The Kalman filter is also found use in modeling the central nervous system's control of movement. Mathematically, Kalman filter is an estimator that predicts and corrects the states of a wide range of linear processes. It is not only efficient practically but attractive theoretically as well. Precisely the optimal state used by the algorithm is found with smallest possible variance error, since it is a recursive algorithm. So let's see how the Kalman filter is actually used in tracking objects in videos. The Kalman filter tracking algorithm involves two steps: the prediction step and the correction step, which is also known as an update step. At first, the initial step is calculated using the previous states. In the second step, current measurement, such as object location, is used to correct the state, and hence Kalman filter implements a discrete time linear state space system. So, if in the case of tracking an object in a video, the first phase is the prediction of the next state using the current set of observations and update the current set of predicted measurements. The second phase changes the values according to the values predicted and gives a much better approximation of the next state. Now the filter involves four parts. The first part is known as the process equation, which is shown here. In this equation, xk represents the object in motion and k represents the discrete time. The aim is to estimate the xk from measuring zk shown in the following equations. A is the transition matrix and xk is the state from time k minus 1 to k. W is the Gaussian process noise n. And this is the second equation, and where P of W is the normal probability distribution. The second phase is nothing but measurement equation. H represents the measurement matrix Vk, is the Gaussian measurement noise, n with normal probability distribution P of V. And the third step is the time update equations. As xk is not computed directly, the measured zk gives results that can be used to update xk. So estimate of the state and the covariance error estimate is obtained in the following equations, which is estimate of the state and the covariance error estimate. The fourth step is the measurement update equations. Here is where the measurements are actually updated. Now the estimate of the state is made as the a priori estimate linear combination of new measurement zk. The equations are as shown below. The gain of the filter is given by kk in the above equation, which is dependent on the noise covariance R. Pk is measured after the a posterior estimate in equation 2, and the measurement equations are calculated repeatedly with previous estimates to predict new ones. This recursive characteristic of the algorithm is what makes Kalman filter algorithm special. Now these are some of the test cases I've used to compare both the algorithms, the mean shift algorithm and the Kalman filter algorithm. Here is an example of a 320 into 240 pixel density video which has a frame rate of 25 frames per second. It is actually a ball undergoing translational motion. So the first case we considered is a ball under translational motion, only translational motion. So here we actually select, this is the detection that is observed by the mean shift algorithm. Here the object to be detected is first selected using a rectangular shape. Then you can see the object being detected in the subsequent stages. The same ball or the same video is tracked, the same ball is tracked using the Kalman filter approach. As the ball goes up and down, it's actually being the actual boundary or the contour of the ball is shown by the green circle, and the tracking done by the Kalman filter approach is shown by the red circle. So the ball is being perfectly detected in the stages, as you can see. Now the second case I've taken is the translational as well as gravitational motion. That is when a ball is rolled off a table and it actually falls down. The mean shift algorithm tends to track the ball normally, and the mean shift as well as the Kalman filter algorithm, tends to track the ball under translational motion, like we saw in the previous case. But under gravitational motion, the mean shift algorithm fails to track the ball, whereas the Kalman filter continues to track the ball even then. Now I'm going to show an example of the mean shift tracking algorithm tracking a ball under translational motion. I choose the target. This is another example which illustrates the tracking using mean shift algorithm of a ball which is under the translational as well as gravitational motion. This is the video of a ball falling off a table. As we can see, it stops tracking the ball as soon as it falls off the table. So it fails tracking when the ball falls under the gravitational force. Now let me show an example for the Kalman filter algorithm. The same ball under translational motion is shown. The green circle represents the actual boundary of the ball, and the red circle is the tracking done by Kalman filter algorithm. This is the plot of the x and y coordinates of the moving ball versus the frame index. Now getting to the conclusion. Both the mean shift and Kalman filter tracking algorithms have almost the same performance when it comes to only translational motion, like the translational motion of a ball. Except that the Kalman filter is slightly faster, as can be observed from the elapsed time. So the Kalman filter algorithm is a little faster than the mean shift algorithm. In case of motion of objects under the force of gravity, the mean shift algorithm fails to track the object, where the Kalman filter succeeds in that too. Mean shift algorithm doesn't use the target's motion direction or the speed. So when there is an object which is moving at great speed, the the algorithm easily fails to track the target, like a fast moving car or a person. So a new object tracking algorithm combining mean shift algorithm and Kalman filter algorithm or motion vector analysis is used nowadays to improvise the mean shift algorithm. Mean shift algorithm also fails when the color distribution is similar for the object and the background in the tracking surrounding. This is because the color histogram is what is used by the MSA to track an object. So when the color distribution is the same, the correspondence of the image object to be tracked in the image cannot be done properly. Hence, Kalman filter approach proves to be a better tracking algorithm in many ways. Here are some of the references that were made during the project. Thank you.